So welcome everybody there and over there online, if there is anybody watching me. I'm Falcou. I will be your presenter for this talk. We will be talking about a bunch of subjects, but we are going to talk about how building libraries in C++ can be made better, simpler, or give better ergonomics, okay, by trying to see what kind of lessons we learn from writing our own long-lived library project. So just so for people that probably don't know me yet, I'm a computer scientist researcher at the this thing. So the how to turn that into English? Digital Science Multidiscipline Laboratory near Paris, and I'm also co-founder of CodeRecons, which is a company that deals into trying to teach proper C++ to people and companies. Libraries, and more generally software tools, is something that is at the heart of what we try to do and to use whenever we want to build complex software. And it turns out that tools making is a very old tradition, let's say it this way. We are now today accustomed to having this software revolution be spearheaded by the Silicon Valley, but turns out I'm actually from the original one. So for people that doesn't know me, I'm coming from France, and more specifically south of France, okay, which is actually the original Silicon Valley, which is the first place people actually try to use CDSAT-based systems to build things, to do useful things, mostly Flintstones, obviously. So jokes aside, the ergonomics in the title doesn't is not centered around how you should be using those Flintstones to do whatever task you need to do with Flintstones, but just to remind us that making tools to make day-to-day tasks or complex tasks easier for people is one of our fundamental human traits. We are doing this since this much, okay? And what we are doing today is not very difficult, just that our Flintstones just went very, very thin, okay? Very, very thin, but we are still doing this, okay? So instead of having to get huge piece of Flintstones to smash bones or to cut off meat, we have very thin slice of flints that can do computation whenever they get struck by lightning. Okay, so this is probably where, as I say there is probably a joke about, like the Moore's laws being right for 10,000 years or something. More to the point. Yes, we like to do tools because it makes our life easier. Okay, but it's a bit like who watches the Watchmen? Who cares about the sanity and the well-being of library makers, okay? Who is doing this? We build libraries because we want to avoid with writing complex code, with writing complex algorithms, so you can actually give some other people something that just works, so they don't have to go through a phase of, what is this thing? Why is it working like that? Why don't I understand what's going on? And so they can get better, they can go faster to their end goals of having something that works in their software, in their more complex systems. So we want to write libraries. And so sometimes it happens that those libraries are written in C++. Yeah, nobody's perfect. C++ has this very long tradition also to be, this close to the metal machine, which is language which is still able to give us very high level of abstraction and whatnot. And everything is supposedly baked by the fact that our compilers are very efficient at optimizing our high-level abstract code, and this notion of, zero-cost abstractions. And this elusive zero-cost abstraction state where you wrote code which is as high-level as you want, so people can understand what's going on in it, and you can actually apply it to complex tasks, still gives you good performances. And at some point, along this path, someone goes and says, oh, yeah, I know. We should use templates to do this. And that's usually where things start to be a bit complicated. Okay? Not because templates are complicated, they are, but that's not the problem. It's because they are a very rich subset of the language, and we need to know how to navigate that. And we did that a bunch of times. I'm still doing it. So we wrote different kind of libraries. My main research topic being high-performance computing. They all gravitate around that. But this is not the main subject there, okay? The thing is, to write those libraries, some of them for decades now, we went through different phases. We tried different approach to how to make the library good, so library writings good, okay? So users, power users, or other contributors can actually, you know, do something with all of that. And yeah, we went through different paths where basically stuff were working, but not fast enough. They were compiling, but not fast enough, or they were just plain, you know, we weren't able to actually explain what's going on, which is usually bad when you write software. So we try in this talk to speak about the stuff that worked, how they shaped some part of those libraries, okay, and what kind of more global nuggets of knowledge we can extract from that, and why and how we made that so we think we ended up with something which is easy to use and easy to develop with. So that's the goal, basically, of this talk. So no more Flintstones. Sorry for the Flintstone enjoyers in the room. One thing that we sometimes forget is that designing an API for software, for a library, it's actually the hardest point, okay? Usually we know how to fill up the libraries with whatever the functions or the objects are supposed to do, but providing a proper API is complicated. And it's as complicated as your target audience, let's say, has different level of, you know, understanding of the software, different, you know, expectation for what they should be able to do with your libraries. And as I said, we focused on high-performance computing. And basically, if you want to have any meaningful impact there is a bunch of rules you try to follow. You try to be non-disruptive because, you know, people that do high-performance computing, scientific computing, they are mostly scientists before being computer scientists. So they have their habits. They like to do the things the way they were doing it before. So you don't want to, you know, change too much of the same thing at the same time for them. They usually work with very specific domain-driven application where some specific optimization are paramount to be done at the right time. So we need to have a way to do this. The API, again, should be intuitive because you are speaking with maybe physicists, statisticians, biologists, you know, people from mechanics and stuff like this. They understand roughly what the software is supposed to do, but what they want to express is what their domain is supposed to do. Obviously, nowadays, you also want to go fast, so you want to be efficient as a whole, and you want to be able to support whatever new architectures someone is actually slapping on your desk. So what we decided to do is to do the obvious things. If you want to be non-disruptive, if you look at what people do, most people do C++. So let's have C++ libraries, which is good because if not, I won't be making this talk here, okay? And C++ also solves a part of the efficiency issues, or so we think. Domain-driven application means that you need to have your library to be able to express the domain relationships, the domain elements in a clear way. Traditionally, one of the solutions to do that, it's not maybe the best one, is to design your library as small languages that mimics whatever the original domain is supposed to do. Doesn't mean you have to go full-blown, you know, like expression templates or whatnot, but just carefully choosing the name and the way your entities are going to be manipulated so people look at the code and say, oh yeah, I recognize my formula, I recognize my way of thinking, it's good enough. We are not going to speak about this, but this is an important part. We need to have a way to abstract away the problem of parallel systems. So all the architectural, supports can be done properly, but that's another subject, but it's also something important. And back to the efficiency issue, we wanted to be able to use the most parts of, what generic programming is supposed to give us and what generative programming is supposed to give us. Because I know I can write some code that go fast enough once or twice, but if I need to do that all over again for different situations, if the compiler can write it for me, be my guest. So we are going to try to do this. Okay, fine. So there is some word that gets slapped there. So we speak about intuition, we spoke about extensibility, or at least this way of, working on different kind of systems and whatnot from now and in the future. But what do we mean? Well, by intuition and by intuitive API, what we mean is that, again, the user should see stuff in their code they know about. Okay? They should be able to reason about the code the same way they would reason about the math they wrote on a piece of paper or the graphs they write on a blackboard or something like that. Something else, which is, I think Eric Nibler said it the first time, or I'm not sure he's the original author about this thing, but you want your API to be easy to use properly, and you want it to be hard to use incorrectly. Okay, so you need to find a way so that when people try to write stuff that makes no sense, to have the compiler tell him, no, you shouldn't be doing this, And incorrect usage should be reported early. And early means basically that you want to have as much compilation errors driven by logic error as possible, and you want them to be clear. And that will be one of the biggest hurdles we are going to speak about. And your components, your libraries or your sub-libraries or your classes should have a single intent, a single responsibility. They should be doing one thing well and one thing only. One issue we had in another bunch of library we designed, we ended up with a proverbial, kitchen sink library that was doing everything, from doing some computation to cleaning the tiles and putting kids to bed. And in the end, it was a mess to make, a new version of it to make it evolve correctly. So we went back from these monolithic designs. And so if you are not a big monolith that do everything, you need to have a way to extend yourself. And this is a different matter, because depending on which kind of user you are speaking about, is it your regular users that just want to use the library and do whatever you advertise it should be doing, or your power users that want to do that, but they have those corner cases that are very important to them, and they want you to support them, and your contributors and the other developers of the libraries that want to be able to add or modify whatever the library does. For the user, what you want to do is you want the user to be able to combine your API and get predictable results. Okay? For power user, we need to have a way to say, okay, we understand that these corner cases of your issues, of your domain is important, but it's a corner cases, but this is what we propose you to be able to have some kind of escape hatch to go back and explain us what you really want to do. And for your contributors, we want to have a dead simple way to say, I want to add a new something in the library. This is a process. Okay. Yeah, quite a bunch of things to do. So let's start by looking at a bunch of those questions in the context of Eve. So quickly, Eve is a SIMD wrapper that lets you write portable SIMD instructions with a bunch of functions, algorithm. If your CPU has a CMD register set, we probably work on it, or we are going to work on it. It's liberally licensed, and I want to emphasize that again. It's a huge teamwork for multiple people, myself included. It's somewhere on the internet. You can play with it. You can tell us that we do bad things. We are very keen to getting returns of opinions. But that's not what we are going to speak about. Let's have a look at what kind of things we can write using Eve. Eve is designed to rely on a very few number of types, and most of the rest of the algorithms and the operation you can do on these SIMD registers, those large registers containing multiple values, is done through an abundant number of free functions. Okay, fine. Free functions, first thing, free functions are your best friend because they can be extended, they can be overloaded externally from the main library. So it's less complicated than modifying those than having, you know, something based on member functions. And you can actually see free functions and member function as being on the same level of an API description level. Okay. But, yeah, it's not that simple. Well, we can do simple operations. So we have this plus thing going on. So, for example, if I do this C equals C+4, what I am actually doing is I'm broadcasting the 4 and adding it to every lane of the register. Okay, so this is a horizontal parallel processing. But if you look at what hardware are giving you nowadays as options, some hardwares, not all, have this. Where is my cursor? It's over there. Okay. Have this way of to say, oh, I want to do this addition between C and 4, but I only want to do it if A is less than B. So we can actually have masked operation. It's not something every hardware do, but a lot of them do it now, and more of them is going to do it. So it can be a mask, like every lane you can say yes or no, you want to do something. If you do, for example, GPU computing, it will remind you of something. You can also decide to ignore some parts of the lanes, okay? So we can say that I want to do the multiplication except for the n first or the n last value. And that's already something we need to find a way to pass through as a function without having to disrupt too much of what people expect to be writing. Some other hardware has variations of given functions. Maybe you want to do saturated operations. Some CPU provides that. Maybe you want to be, you know, you want to go fast because you are using SIMD, but you want to go fast, but be sure that the results are correct. So maybe you want to be able to say, okay, I'm okay sacrificing a bunch of speed so that we can have extra checks for corner cases, like probably, you know, like nonce or whatever, or infinites. Stuff like this. So we know we can have something that makes sense, for example, that is behaving as the same way as what the standard version of the function could have done. Or maybe you want to do the opposite. You want to get to the fastest version of the function that is possible to have on this given hardware, and you don't care if you lose half your bits of precision or if you don't handle nonce or whatever. So we need to have those options. And so the thing we did was to have this kind of notation. So we have something that looks like functions, because this add, this x stuff, it looks like a function. But you can actually slap them some of option using these brackets, okay? Those brackets can be combined. In C++23, obviously, you will be doing the variadic brackets, but that's another point. And so the question is, how could we make that work? I mean, the answer is rather easy. You want something that behaves as a function, but you want it to have another piece of API, this bracket thing, so it's probably just a callable object. And as soon as we go there, we're, oh yeah, callable object. We know how to do this. There is plenty of, you know, writings on the subject. We can probably get something running from that. Yeah, yeah, probably. Let's try to dissect that. Because basically, every one of those functions has between 2 and 10 overloads, depending on the architecture, the types, the operation you want to do, the optimization you want to apply. Are they masked or not? Some combination of operation and types needs to be emulated because on this particular hardware, well, there is no such function. So we have to make it work anyway, somehow. And the specific optimization that we may want to do, either through an actual options or through a reinterpretation of the function call, need to be done also under that. So at some point, for some silly functions, like just taking the additions, on the 3 different main architecture sets, we were ending up with 55 or something overloads just for add. So we cannot just have 55 overloads living like that because, I mean, your compile time will be a mess. So moving to callable objects was the first part of doing this, but we still need to dispatch to the correct things. Now, if we do this, enough, patterns start to appear. So we wanted to be sure to capture them, so we don't have to rewrite the same classical ending of some situation for every function. So we reuse some kind of skeletons for the callable object, so we can just say, okay, this one behaves that way, and I just, focus on the small part that changes. We decided to obviously use concepts for ensuring function calls validity. I'm not going to call cost on an integer. I'm not going to call, power function with non-proper, proper types either. And this was something we wanted to do right at the beginning of the project, which started just after the C++17 standard. G++ back in the day had a starting part for writing with concept. We started rewriting the library in C++17, and someday I decided to test concepts in the trunk from GCC, and it was so good we just decided to put the whole thing into C++20. Another thing we try to do is to try to turn architecture detection into context-aware information instead of relying on if-def and stuff like this. And if context-aware was also a big mover in these things, so we could actually use if context-aware to select between different variations of functions. So the question is how all these ideas went through. Well, let's start with the first part, which is callable objects things. Whenever you build a new functions in these systems, there is a lot of scaffolding you want to do. If you have a function, like for example add or the absolute value or any of those mathematical functions that basically behave the same way lane per lane, it's a very regular systems, you know that you have a lot of things you want to be doing with them, and then you can free write without having to think about it. You want to handle the broadcast of when you mix a scalar and CMD values. You want to be sure that whenever you have this masking thing going on, you can actually know if a masking is actually occurring or not, because if it's not occurring, you can simplify the code. And for some other function, you want to be sure that conversion are not allowed. You want to explicitly prohibit mixing with scalar. You want to behave like a constant. You want to behave like a reduction function. So at this function level, we were basically confronted to all these, basic things we didn't want to rewrite again. And those similar behaviors were put into pre-made callable objects that we can just reuse. And at the very beginning of this, we had a system that was basically looking like what the task dispatch system was supposed to be at some point. Having function object, jumping into, external functions that you could actually find out by ADL and whatnot using tags and stuff like this. Turns out, it physically works in the sense that when you make it run, it runs, okay? But as we are going to see a bit later, was not that good. So the idea was okay, but the implementation was bad. So we made an ad hoc specification of that. And at first, that was very centered on what we were needing to do. And then afterwards, we kind of find a way to make it more usable in a more large concept. So basically, what we want to do is we want to write, let's say, the apps function object. And this is it, basically. So what do we have? Function objects in Eve are basically an instantiation of a template type. So these ABST types, which take a single parameters, which is information about which kind of options is currently applied to the object. So whenever we do a bracket, we are actually generating a new function object. So this contains the semantic options, okay, in compact forms, okay. The option types is basically some kind of record tuple-like object. Every callable should inherit from one of our predefined callable things. So this is element-wise callable, which basically says that ABS works lane by lane, supports masking, supports combination with different types and whatnot. And if you have a quick look there, so we find the option back there, and we have another set of things there called saturated options. So the end of this class is actually a variadic list of every option the object is able to support. So we can basically say, okay, I'm supporting saturated, and that's all. And if you call me with any other option, I won't let you do it. And so this base class basically do everything else. What do we have next? Well, we have a high-level user-facing concept on the function call operation. Now that I see it, I should have taken another function because this one is actually not very interesting. But so the value concept basically means that you accept any kind of arithmetic-like scalar or SIMD values. Okay, we have stuff like floating value, signed integer values, product type value, and whatnot to differentiate the different things we do. And the cool thing is, we are going to see how it works, but the implementation is always the same. You take your parameters, compute your return type, and you do this macro thing, okay? Turns out this macro is actually the one place where having a macro makes sense, so we are going to probably keep it for a long time. So whatever you do, you just forward, you pass your parameters to the dispatch call macro. And then we have some kind of another macro there that actually registers the object as something tied to an external function that will do the actual computation. So whenever I'm going to dispatch my call, whenever I'm going to dispatch my call to something, I will end up into some ABS underscore function that is supposed to await us in some very specific namespace. And in the end, well, we use this functor inline template object to turn the type into the actual callable. Okay, it sounds a bit long. We should keep explaining it, but it's actually something that, if I go back to my power user developer scale, our contributors handled quite well. One of our main contributors, Jean Thierry, which is a mad guy first. My main issue is actually having to keep up with the pace at which it adds function using this model to the main library. So it's something that you can get accustomed to. We have a large subset of examples you can derive from. And the fact that this scalable system is actually open-ended by being external types, it happens that sometimes the one we have is not doing what we want, so we can just add another one for the specific case and go back to this model. Different things are important there, and we are going to speak about them. First, you want to have your function or your function call operators to be validated by a concept at the higher level possible, closer as you can to the user calling site. So we put it there. You want your return types to be as clear for the user as you can. We could have used auto. We are going to speak about the issue of auto as a return type a bit later. But most of the time we try either by having something clear like that or having a small thread next to it to compute the exact type we are going to have. And that's something which is also important. Side bonus, as every function in the library is actually an object, you can just use them with whatever kind of algorithm you want because they are already an object with a function call operator, so you can just transform using if abs or if add or whatever, and you don't have to put a lambda around it. Okay, yeah. What is inside this callable skeleton? As I said, we have a large number of things we keep doing on different versions of the function, ending the conversion, ending the emulation if there is any, ending the broadcasting. And so we didn't want to repeat that every time we write a new function. So we put that into those scalable things. They help us to have these recurring code patterns down into a box, and it always also helps us streamline the error checking process at the type level. And as they are actually built as a loose succession of classes in an externally defined hierarchy, you can actually extend them as much as you want. And the simplest one is a callable one, which basically do the minimum amount of things. It handles the options. It has this behavior function that we just turn the operator call into the actual function call. And we have this retarget function that basically do the same, except you force the call to use a given subset of specific architectural options. So sometimes you want to call something, you are on this architecture, but you don't know how to do it, so you go to the less specific architectures above it, and you can retarget your calls. And every callable has this shape, basically. And this behavior and retarget function are actually dipping into those macro we saw earlier, okay, which ties the type there to the actual external function that is fetched through using ADL. So somewhere else in the if detail namespace, we have something like this that will do the actual computation. And so we have this object, couple of macros, and we have this easy to slip, jump from the call to the actual implementation. The actual implementation itself uses if-const-expr like a lot, if I can say that, by basically turning it into some kind of compile time match, okay? So we can take our types, find information about them, and just say, okay, I use this one, I use this one, I use this family of types, and for whatever we have, we can have a very specific implementation. So, absolute value on unsigned is the identity. If I'm a floating point, I have a formula. Sometimes I have an intrinsics, and sometimes I need to do different optimization, and we can just pile them up using if-const-expr. ABS is like 27 steps of if-const-expr in a single function overload instead of having 27 different overloads for the same function. Okay, fine. Now, what happens if I do a mistake? I'm calling this function with the wrong thing. Well, let's have a look. So one thing we learned, how to say that, at our own expense, is that it's not easy to write this correctly from the first time. So this is two versions of the library, the old one and the newest one, okay? I'm doing something stupid, okay? I'm calling cost on an integer. That's not something we support for some reasons. And so this is what I have there with the old version. So first, and this is very important, we did something right on the first time, which is whenever you have an error because your user called the function incorrectly, you should make your implementation based on concept or whatnot, so that the error is actually reported by the compiler at the call site in the user code. If your library tells you that, oh, you did something wrong and include something, detail something, some files.hpp, this is not whatever, you lose the game. Because what will the user do? It will see this massive or not massive error that it doesn't understand with the finest link to its own code, and we go, okay, I tried to do something that for me was correct, something bad happened, the error happened in the middle of the library, conclusion, the library is bad, I'm going to move and find another one. Whenever your your user of the library do something wrong, the error should come from its own code, okay? So that was okay. Now, what's the error? Let's say you don't understand, you don't know what you're doing. Why am I going wrong? Well, yeah, stuff, other stuff, okay, right. Yeah, yeah, I'm not a floating point. Okay, so where am I? Like there, okay, I scrolled like 1, 2, 3, 4, 5 times. So it's not very usable. Litmus test, okay, if your error message needs that to be intelligible, no bueno, okay? It's not going to work either, okay? Because nobody knows about that, okay? And so hopefully it's there, because if not, I would have missed all this non-information, okay? Well, that's the old code, okay? Let's recompile it, because this one is a cache version. And when it compiles, because that's a cool way when you have a slow compilation time, you can do something else. Let's have a look at the new systems, okay? So the first old system was a direct implementation of the tag dispatching systems that were proposed time and time again during the standardization of a lot of things. This one is our ad hoc things. So first things first, we have less cruft there, okay? I mean, the error message, okay, which was what I call the, this is what I call the, God ball bar size metric. It's far better, actually. So we still say that the error is the user code, so that's cool, okay? It comes from this, okay? Oh, it comes from when I call the function, oh, some constraint is not satisfied. Oh, yeah, it's not a floating value. Okay, because, yeah, of course, int, it's not a floating point value, you know? So it's still a bit rough because GCC tries too hard to give us information, but we can be, you know, too much against that, okay? So yeah, the time to the actual error is shorter, okay? You know what's shorter? So this is the compile time of the old version. How much is that? 8.5 seconds. I'm just calling cost. Okay? What's the time on the new version? Okay. Yeah, it's probably half of it. Yeah, it's like 4.3. So we shaved half the compile time just by reorganizing the way we are dealing with the concept and we are dealing with the jump into the actual implementation. Okay, the code is the same anyway. We go faster there. Okay. So this is actually important. You want your error to be in your user code. If not, the user will think you did something wrong. And you want the time to the discovery of the source of the error to be as short as possible. Now, one thing we learned, one reason why we have this roller coaster of information there, is that somewhere in the old code, we were using auto as a return type. Turns out if you do that, and I mean regular auto, not auto decal type, just auto, right? If you do that, the compiler has to compile whatever is inside the function to know what it has to put on auto, and you keep having this cascading error because obviously your code is bad, so the return type is bad because it was bad there, and it was bad there, and it was bad there, up, down to your thing. So it turns out that you can use auto. We use auto a lot in our implementation. But as soon as we go up there, I'm just going back a bit. This better be to be an actual real type or a computable types. Okay, so fine. So having this concept upper in the call stack with less reliance on automatic type deduction, we basically shave the compile time, and we basically also shave the length of the error message. And as I said, you should not report error from the user inside your library. Another trick we use is what I call the ignore trick, because sometimes, well, you have to return auto for some reasons. Okay, I'm trying to see if I can zoom a bit on that. Can I? I can. Okay, can I close this? Yeah. So we have this type. So this is one of another callable, strict element-wise. So it's like element-wise, except as the name implies, it's stricter, by the means that it doesn't allow automatic conversion and whatnot. Okay. So what we do there is that we need to know how we should be calling the function, and we have different ways of doing it. I mean, maybe I have an actual implementation, so maybe this thing is working, so I will just call it, if it happens to be there. If I have no implementation, maybe I can, try to emulate it by doing the computation piece by piece. Maybe I am actually all emulated already because I am on an architecture that doesn't support a given type, or maybe I have larger registers that the hardware is supposed to be handling. So we check that, and what we do is, okay, if I am bigger, for any reason, I'm just calling handle the bigger case, that we basically slice the big register into the smaller one and call the function again. Okay. If I need to go through map, I go through map. And if I have an actual implementation that does the right thing correctly, I'm just going to call it. And we could have stopped there, but if you stop there, if you forgot an implementation, or you miswrite it, you permute an argument or whatever, you will have a massive, ugly error message in your library, which is bad. So what we do in the last case, we just return ignore. Ignore is an empty type that is convertible to whatever, doesn't care. So if you put it into a variable, it will probably say, yes, okay, I'm going inside, okay? And what we do in the behavior of this, okay, let's just focus on this part. I'm trying to see if I can call my function directly. So I'm trying to check that the return type of adapt call is not ignore, because if it is ignore, I'm just static assert that, okay, you just forgot to write the function, okay? And if not, I'm just returning that call. But even if I have this static assert, if I didn't have ignore, and I just have void or any other bad types, the fact that we return that call after a while will have triggered a cascading error. And by returning ignore, we return a type that the compiler knows about. It has the most stupid semantic, but it's enough to be able to be assigned to whatever your user code is doing. So you won't have any more errors than, oh, yeah, you forgot to implement this function. Stop. So we use this kind of empty type tricks to do, okay, we have an issue that we need to static assert upon because it makes no sense, but we return this type so that the rest of the computation is going okay. And speaking of my slides, okay, where are you? Oh, okay, I did this. Okay. Yeah, I'm a professional. Okay, don't do that at home, okay? Yeah, sorry for that. Speaking of static asserts, when should we use them? What we find out is that you want to use static asserts the same way you use assert. A logical error occurred and you want to report it. I mean, we don't use them to say, oh, you call this function with the wrong type. We don't do that. What we do, now that I know how to control click, where are you? Yeah. So let's have this function. So RSHR is basically a right shift with a relative amount of shifting. So if you put a positive number, you go to the right. If you put a negative number, you go to the left. Obviously, you can call that with two dynamic values, but you can also call it with a statically known number of shifting bits. And obviously what we do is that you have the right to call it this way. It's a okay-ish call, but your value is nonsensical. So the same way we have an actual runtime assert when you call it at runtime, if your shifting amount is bigger than the size of the bits of your types, we have a static assert that say, okay, you try to shift like far too much, okay? So yeah, because 100 is not smaller than 32. And that's exactly what we want. You don't want that to be finite out or get rid by a concept, because the call is right, the value inside is not. The fact that the value is known at compile time is a detail. Your value was bad, it makes the logic of the function wrong. The fact is that you want to assert, but you can assert at compile time because you have more information. And that's where you want to deal with static asserts. Even if it breaks the fact that your function won't be finite friendly anymore, because you will report that the function is scalable while it's not. But in fact, it is scalable, just as the result makes no sense. So, what did we learn of all of that? So concepts are important. Just use them if you don't already, but it's 2025. I hope everybody is actually using concepts when they can. But you need to use them properly. You need to use them to dispatch over types capabilities. Is the type that come in my function has the right API to do what I need to do on it? If not, either I have another one, or I will just forget about the function altogether, right? You should be using ifConstExpert to handle implementation detail variation detectable at compile time. You don't want to overload or to use concept overloads to select between different implementation. Selecting different implementation is a job for ifConstExpert. You want the least amount of overloads. But inside each overload, you can have the most complicated pattern of things. You want to filter out the bad calls as high up as you can into the call stack. And as such, concept reports API misuse. You want to use static assert to report compile time logical issues. And what you want also to do is to be as finite friendly as possible. You want your function to be able to be detected as callable or not, so that you can increase the potential reuse of your library in other components, okay, in a way that minimizes dependencies. And starting from all of that, at some point, we decided to check if we can go like a bit further in whatever we want to do. And we tried to apply what we saw already and what we thought was a good idea to another kind of. Yeah, so now we have like a less bright sun spot on the screen. So, what if we try to apply that to another kind of libraries? Another thing we do Because we do computation, but maybe you know that if you want to do computation, maybe at some point you need some kind of data somewhere, okay? So storage data in high-performance components is its own huge problems. Am I going to need an array-like owning things? Do I need a view? Do I need to be able to have my dimension known at runtime, at compile time, both? Am I monodimensional? Am I multiple dimensions? Am I store like C, like Fortran, like whatever? What is my starting index, and so on and so forth? The joke we have with our good friend, the physicist, that if you ask 10 people what they want in their data storage library, you probably have 12 answers, okay? So it's very complicated, even if it doesn't look like that. I just want to have a multidimensional array. What can be hard in that? Well, the fact is all of that. And the problem is, the random user will have the need of having a random number of options set up for their containers. If you try to make a monolithic implementation of that, again, it leads to unmaintainable code. We retired one of our libraries just because of that, because the cost of adding stuff to it was going exponential. Arbitrary restriction on the API, like we always do owning and it's always Fortran style and you can choose whatever, is usually not a solution because people will just say, yeah, so I don't care about your library, I'm going elsewhere. So can we get creative a bit and get something that works? That we try to do. So that's what KIWAKU is dealing with. So it's the C++20 and onward multidimensional storage container library. We only deal with storage. We don't do computation. We have algorithms, but we don't deal with linear algebra or whatnot. We just apply whatever on the whatever data. Okay? We wanted to start from scratch, starting with the new features from C++20 and 23, so we can see how far we can go creatively on that. Again, it's a teamwork with a lot of cool people, so special shout out to them. So what do we have? We have containers and traversal algorithms, which are basically extension into n dimension of the standard algorithms. And again, we wanted to be creative in the way we use concept on one side and other new C++20 things like extended compile time computation capabilities and non-type template parameters. So yeah. How does it actually look? Well, we have two types, view and table. These are basically n-dimensional array, owning or non-owning. So view is non-owning, table is owning. You can wrap memory into NDL array-like interface and whatnot, and both of those containers are designed so that what I call the resting position, so you just have an object of this type with nothing inside is the smallest possible. That's something people actually care about at some point. And the cool tricks we find out is that the table is actually just a view over some data it contains itself. Okay, so table inherits from view privately. It has some kind of buffer-like object inside, and the view points to the buffer inside the table. So as long as we have a good view, we have a good table, because it's the same API anyway. And yeah, how do we construct such a container? Again, we are facing this issue of, far too many options. So how do people can, how to say that, choose what they are going to do? So the idea is to have a way to abuse, that's the word. Yeah, we abuse user-defined template deduction guide, like there is no tomorrow. We use another library which is called Rabero, which is basically let us having, named parameters. And we construct our object with this series of named parameters that say, okay, this is the data, this is the size, this is the whatever. And we pass everything as a const expert object to a CTAD that computes the exact type by doing some stuff. And as soon as this NTTP is computed, we pass it as a parameter of the internal implementation of the container and just construct the API from that. So it's a bit like CTAD are actually are actually Turing complete in the fact that we can do some kind of computation over types with them. Good point, you can make the constructor as cool as you want. Less good point, yeah, symbol names. We are going to have a look at that. It's something, Okay? So this is alpha success, let's say. We are working on it, but this is alpha success. So it looks basically like this. Okay, so it's okay in the back? Yes, no? Okay. So we have these view things. And basically, I mean, you can look at line 11 to 14, and even if you don't know what the library is doing, you probably understand what is going on. I mean, I'm fetching some data sources. I say that it's like a 2 by 3 by 3 array, and I will put it a small name on it. Okay? I will call it raw data, okay, right? And so this constructor do everything, and you see that I'm just using auto there, because there is no way you know what to put there anyway. And view is used as some kind of high-level construction there. So it's a 3-dimensional array. I can do a 3-dimensional loop and put some stuff in it. I can print it. And as it was a view over the vector up there, if I look at what data I have into the data vector, I actually have whatever I did there. Okay. Oops, sorry for that. Yeah. Okay, fine. And you see that I have this label. This label is actually printed out when you print the thing. That's something that was asked also. Okay, fine. Well, what did I say about the symbol name? Oh, yeah. They require, how to say that, some work. So let's have a compilation error there. So we can have a look at what VD is actually. Probably need this space there. Okay, whenever you want, internet. Yeah, okay, yeah. Apparently, I cannot convert the green stuff into the blue stuff, okay? And so you see that we have these builder things going on with these settings things that do whatever, 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 whatever. From this thing, whatever, 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 into void pointer. Yeah, okay. So I'm a bit mean because where is the end of the name of the type over there? Yeah, there. Okay, no, I'm not mean actually. Yeah, I am not. So I have all of that going on, okay? Yeah, that's something we are trying to work on. Basically what we need, if anybody from the standard is looking at this video later on, what's the name of that? A type erasure in context per function when. Okay, that's the thing, okay? I just need that. Give me type erasure at compile time, and this is a one-line thing, okay? But whatever. Thank you in advance. If you want another funny thing, okay, you see this. Probably the most bizarre name for a namespace. This is our detailed namespace. We found out that the smaller this thing is in the symbol table, the faster we compile. It's probably not normal, okay, but it's probably something compiler vendor doesn't care about, optimizing, and they are right, okay, just a funny thing. So starting from now, every other library we have, we use underscore as a detailed namespace, so we save like 4 characters per, time we need to do detail of the thing, okay. So that was a funny find, okay. Yeah, so the symbols, yeah, it needs works. We are still trying to find a way to do that better. Currently, with our new PhD students, the idea we have is to go back to a more functional construction thing, so we don't be using CTAD anymore, and every subset of options actually call a different function that return a very specific type, so we don't have this mess of a thing. But it was a cool experiment because it actually showed us that we can have this, okay, this is all the info you need, give me the correct type and do whatever. Speaking of another thing we said, trying to not go over time, resting size, that's an important thing. What's the size of VD? What is this? It's probably a lot there because I have like 3 times size t for the size. I probably have a pointer to the string. Yeah, it's 40 bytes. Okay, let's get some fat out. So let's remove the label. Probably 32. Is it 32? Yes. And what we can also do is that if you know that your size is known at compile time, so we can have this underscore C things. So we don't need to store it, actually. It's in the type. So now we should be 8. Yes. And so that's basically the size of the pointer. So mission accomplished. OK. I'm going to get a bit faster. Sorry about that. We have algorithms. It's basically the ND version of the algorithm over the standard things, except we reorder the parameters so we don't have to write a zip iterator. For everybody that already wrote a zip iterator, you don't want to write a zip iterator, okay? And we have something that looks like execution policy, so we can go over different hardware stuff. So no zip means the code is simpler. Everything becomes some kind of tuple manipulation game, so that's why we have our own tuple library like that. So this is functions. Cool thing is, I don't know what kind of type this is, okay? So how do I make a function taking a table? Well, you can ask using a concept. So what you want is any container which is 3D. The fact is we use the same NTTP we use into the constructors in the concept. So it has to be 3D, but I can ask it to be, oh, you know what? It should also be double, for example. So it has to be 3-dimensional and double. Now it's not, because it's float. It will break. And at some point, what I need to know, constraints not satisfied because, yeah, where is it? Yeah, same as is not correct. Okay, fine. So we can do that. You can have just container if you want and whatnot. So we have this variation, n-dimension variation on algorithms. So generate takes a lambda with that much. Yeah, I know. But you can have other things. So let's just have an example with the wonderful transform operation. So I'm going to output into C. My first parameter is C. My second parameter is C. So the output is there. And then I have a variadic list of inputs, so I don't have to make a zip iterator. And oh, yeah. Having a body in the lambda is actually useful. I reckon that. Okay. Whenever. Okay, and now we have that. Okay, fine. So we have that. Last thing we have is this execution policy that we try to do like the standard, but we find out that the fact that the standard execution policy are opaque type is not useful. So our execution policy follow a proper concept, so you can write your own. And they have this kind of API where you can go with a with thing, a bit like Python. And whatever happens in the lambda is actually all executed at once on the correct hardware. So in this case, on the GPU, so you don't have to pay for multiple back and forth between the host and the device. Okay, fine. Parting words. Yes, I can do it. So let's do that quickly. You want to have function-based API. That's cool. You want to think by shifting from interface class object to concept type value, actually. And you want to have your library to be able to cooperate because you will be sharing concepts. But wait. I know that. That's solid, right? You know, it's basically solid, okay? You should have one job, you should be open, you should do stuff when you are doing derived types. You want to have very specific interface, and you want to depend on abstraction. Okay, fine, but that's for object-oriented programming. But you know what? Well, a type of function should have one type job, okay? Software extension is a core design show. That's what we did with the extension on the callable. A refined interface, a refined concept should complement the base concept behavior. Many specific libraries are better than the general one, okay? And your entities must depend on concept, not types. So basically what we reinvented by not doing it is basically solid, but for generic programming. It's very rough, but I think there is a nuggets of information there that should be dug up at some point. Now, what you want to do, you want to maximize interoperability in between your libraries, okay? You want to make quality of life improvement library, even if they are very small, because they will extract some information from your stuff. And which means that it would be cool if, for example, we had an actual standardized packet manager. This is the 29th time I'm seeing this on camera, but we still need it. You also want to publish and promote your tools, because I think a lot of you there and over there probably have some small-scale library which solves interesting problems and nobody knows it exists because you don't publish it, okay? Motivate your students, your collaborators to make more libraries out there, okay? And again, big shout out to all my contributors and collaborators. And sorry for the overtime. But thanks for your attention, and I will be glad to answer some questions. We have like 10 seconds to do it. But thank you again. Do we have? I don't know if we have an online question. Oh, yeah, we have one, yes.
So, were you inspired by any... Okay, thank you. Were you inspired by any other libraries, and do you have some competitors currently?
Sorry?
Are you aware about some competitors of your libraries? And were you inspired by other libraries like Boost or something else?
We wanted to have a way to express, those issues in Eve. We wanted to have a solution to this simply whatever mess. And the very first inspiration we had was, what is the difference with having this, with this wide type? That's what we have when you have STD atomic, actually. It's the same issue of wrapping a very low-level hardware stuff into highly abstract systems. And while trying to do this, we find out that it was actually a non-trivial task. So we started to look around, and we were quite heavily influenced at the very beginning by what the people from SIMD-E and a bit like what the early work of Agner Folk did on these kind of issues. But it was always a bit the same thing, that it was a bare minimum wrapping stuff. So we wanted to be a bit further than that. So we wanted to have this standardized feeling, okay? You have a type and you have something, and we wanted to be actually at some point like this, like some kind of standardized SIMD things. And we try to draw a lot about how other low-level, hardware systems were used into the standard. And then we drove off, because at some point it was not, we found out it was not the correct way to do that, and we needed to part with whatever the classical way of doing this was. And we went to the place we are right now. But it was a progressive, change. Eve is now like it's 4 or 5 rewrites from scratch. Probably 5, yes. Or 4, actually, yes, maybe. So every time we hit some kind of roadblocks, we try to fix them and try to get a new. But yeah, back in the day, I looked at CD Atomic, I looked at what Agner Folk was trying to do with the VEC library, and I'm trying to push that forward.
I think that's all the time we have.
Yeah, okay, sorry, if you have any other question, you can find me next to a cake or something afterwards.